Picture this. Millions of people around the world believe horseshoe crabs are just another beach creature, stepping around them during summer walks. But here's the shocking truth. These ancient animals possess the most valuable blood on Earth, worth up to $60,000 per gallon. Right now, in sterile laboratories across Maryland and South Carolina, a billion-dollar industry is milking these 450-million-year-old living fossils for their blue blood that protects every vaccine and injectable medicine in the world. While you might think pharmaceutical safety testing involves complex chemistry, the reality is far more primitive and fascinating. Every time you receive a shot, whether it's insulin, a COVID vaccine, or even Botox, your life depends on blood extracted from creatures that witnessed the rise and fall of dinosaurs. These prehistoric survivors hold the key to modern medicine's safety, yet most people have never heard their incredible story. Consider this stunning statistic. A single gallon of refined horseshoe crab blood costs more than a luxury sports car, yet without it, the entire global pharmaceutical industry would grind to a halt. These creatures survived 5 mass extinctions, outlived trilobites and dinosaurs. Yet today, they face their greatest threat not from asteroids or climate change, but from humanity's desperate need for their liquid blue treasure. The horseshoe crab industry began by accident in the 1950s, when scientist Frederick Bang discovered something extraordinary about these creatures' blood. Unlike human blood that's red with iron, horseshoe crab blood glows bright blue thanks to copper-based hemocyanin. But the real magic lies in special cells called amebocytes that instantly detect bacterial toxins, clotting around any contamination like microscopic bodyguards. This discovery revolutionized pharmaceutical safety testing. Before horseshoe crab blood, companies used rabbits for toxin detection, a process that took days and often killed the animals. The Limulus amebocyte lysate test, or LAL, can detect contamination in minutes and became mandatory for all injectable drugs worldwide by the FDA in the 1970s. Today's horseshoe crab biomedical industry operates on a scale that would astonish early researchers. Companies like Charles River Laboratories and Associates of Cape Cod process over 600,000 crabs annually across multiple facilities. The industry produces roughly 50,000 liters of LAL reagent each year, with pharmaceutical companies paying up to $15,000 per liter for the refined product. The economic importance extends far beyond the laboratory walls. This blue blood ensures the safety of insulin for diabetics, chemotherapy drugs for cancer patients, and vaccines that protect millions of children. Every major pharmaceutical breakthrough depends on these ancient creatures for final safety approval. From Pfizer's COVID vaccine to breakthrough cancer immunotherapies, not a single injectable medication reaches market without passing the horseshoe crab blood test. The horseshoe crab harvest begins with the full moon cycles of late spring and early summer, when these ancient mariners emerge from deep Atlantic waters to mate on sandy beaches. Licensed collectors, often multi-generational fishing families, know exactly where and when to find them. Delaware Bay, stretching between Delaware and New Jersey, hosts the world's largest spawning population, with over 400,000 crabs participating in this prehistoric ritual. Professional collectors work in teams, wading through shallow waters during high tide when crabs are most active. They carefully hand-select specimens, prioritizing larger females that produce more blood, while avoiding smaller males and already spawned females. Each collector can gather 200 to 300 crabs per day during peak season, loading them into specialized ventilated containers that keep the animals alive and stress-free. The selection process requires remarkable expertise passed down through generations. Experienced collectors can instantly identify the healthiest specimens by examining shell condition, movement patterns, and overall vitality. They know to avoid crabs with damaged shells, lethargy, or signs of disease. This traditional knowledge, combined with scientific training provided by biomedical companies, creates a unique workforce that bridges ancient fishing culture with modern biotechnology. Transportation happens immediately after collection, with crabs packed in damp seaweed and rushed to biomedical facilities within 24 hours. Temperature control is critical. Crabs must stay between 50–60 degrees Fahrenheit to maintain optimal blood chemistry. Specialized trucks equipped with climate control systems race these living cargo loads from beach collection points to laboratory doors, sometimes covering 200 miles of Atlantic coastline. Upon arrival at biomedical facilities, each crab undergoes initial health screening. Trained technicians examine shell condition, mobility, and overall vitality, rejecting any specimens showing signs of stress or damage. Only the healthiest, 80%, proceed to the bleeding process, ensuring both animal welfare and blood quality standards. The bleeding process itself represents a marvel of precision biotechnology, adapted to ancient biology. Technicians position each horseshoe crab in specially designed stainless steel restraining devices that hold them safely without causing injury. The extraction targets the heart area, where a large needle pierces the soft membrane around the cardiac region to access the main circulatory vessel. What happens next showcases the incredible efficiency of these creatures' biology. Horseshoe crab blood doesn't use hemoglobin like mammals, instead relying on hemolymph, a copper-based fluid that carries both respiratory and immune functions. This blue liquid flows slowly but steadily, typically yielding 50–100 milliliters per crab over 24–72 hours, representing roughly 30% of their total blood volume. The extraction environment maintains hospital-grade sterility standards. Every surface gets sanitized with pharmaceutical-grade disinfectants. Technicians wear full protective equipment, and air filtration systems remove microscopic contaminants. Even minor bacterial presence could compromise the blood's toxin detection capabilities, making these laboratories cleaner than most operating rooms. High-efficiency particulate air filters cycle the entire room atmosphere every 15 minutes, while positive air pressure prevents external contamination from entering the facility. Advanced monitoring systems track each crab's vital signs throughout bleeding. Heart rate sensors, movement detectors, and visual observation ensure no animal experiences excessive stress. If vital signs deteriorate, extraction immediately stops, and the crab returns to recovery tanks. This careful monitoring maintains both ethical standards and blood quality. Stressed animals produce compromised blood chemistry. The technical sophistication extends to the extraction equipment itself. Custom-designed needles, manufactured to pharmaceutical standards, minimize tissue damage while maximizing blood flow. Computer-controlled pumps regulate extraction pressure, ensuring steady flow without causing circulatory shock. Each station includes backup systems and fail-safes that immediately halt the process if any parameter falls outside acceptable ranges. Temperature control remains critical throughout the 2 to 3 day process. Cooling systems maintain exactly 39 to 41 degrees Fahrenheit, the optimal range for preserving amoebocyte cell activity. Digital thermometers provide continuous monitoring, while backup cooling systems prevent any temperature fluctuations that could damage the valuable blood components. The entire facility operates on redundant power systems, with emergency generators capable of maintaining operations for weeks during power outages. The collected blood immediately undergoes initial processing, with centrifugation, separating the precious amoebocytes from other blood components. These separated cells get suspended in specialized preservation solutions, creating the raw material that will eventually become LAL reagent worth thousands of dollars per liter. Each batch undergoes preliminary quality testing before proceeding to the complex purification process that transforms raw blood into pharmaceutical-grade testing reagent. Post-bleeding processing transforms raw horseshoe crab blood into the pharmaceutical industry's most critical safety tool. The blue blood undergoes sophisticated purification, involving multiple centrifugation cycles, washing procedures, and sterile filtration that removes all contamination while preserving the amoebocyte's toxin-detecting capabilities. Laboratory technicians create standardized LAL reagent through carefully controlled procedures. The amoebocytes get lysed, essentially broken open, to release the proteins responsible for toxin detection. These proteins then get freeze-dried into powder form, creating stable reagent that pharmaceutical companies can store for months and reconstitute when needed for testing. The purification process involves cutting-edge biotechnology that would be unrecognizable to early researchers. High-speed ultracentrifuges separate cellular components at forces exceeding 100,000 times gravity. Automated washing systems remove impurities through dozens of cycles, each monitored by computer systems that adjust parameters in real time. Sterile filtration through membranes with pores smaller than bacteria ensures absolute purity. Quality control testing happens at every stage, with each batch undergoing rigorous validation procedures. Test samples get exposed to known bacterial toxins to verify proper reaction times and sensitivity levels. The LAL must detect endotoxin concentrations as low as 0.03 units per milliliter, sensitivity levels that can identify a single bacterial cell in a swimming pool-size volume of liquid. Only batches meeting exact specifications receive approval for pharmaceutical use, ensuring global medicine safety standards. Different grades of LAL command different market prices. Basic screening grade reagent sells for $8,000, $12,000 per liter, while high-sensitivity research grade versions reach $20,000 per liter. Specialized formulations for specific pharmaceutical applications can exceed $30,000 per liter, making this among the world's most expensive biological products. The horseshoe crab biomedical industry employs over 2,000 specialized workers across the Atlantic coast, from seasonal beach collectors earning $200 and $400 per day during harvest season to PhD biochemists commanding six-figure salaries in processing facilities. This economic ecosystem supports entire coastal communities, particularly in Delaware, Maryland, and South Carolina, where fishing families have adapted traditional marine harvesting skills to biotechnology applications. Charles River Laboratories, the industry leader, operates processing facilities generating over $164 million in annual LAL sales worldwide. Associates of Cape Cod, Lonza Bioscience, and other major players create a competitive market that drives innovation while maintaining the high standards required for pharmaceutical safety testing. These companies collectively employ marine biologists, biomedical engineers, quality control specialists, and regulatory affairs experts, creating high-paying career paths in historically economically challenged coastal regions. The economic multiplier effects extend throughout local communities. Equipment suppliers, shipping companies, laboratory construction firms, and specialized service providers all benefit from this unique industry. Towns like Chincoteague, Virginia, and Cape Henlopen, Delaware, have transformed from declining fishing villages into biotechnology hubs, with median household incomes rising 40 to 60% over the past 2 decades. The ripple effects extend throughout the global pharmaceutical supply chain. Every injectable medication, from life-saving cancer treatments worth billions annually to routine vaccines protecting millions of children, depends on LAL testing for regulatory approval. This creates an unusual situation where a single species controls access to modern medical treatment, making horseshoe crabs arguably the most economically important marine animal on Earth. Export markets span every continent, with European pharmaceutical manufacturers purchasing roughly 40% of global LAL production, Asian companies accounting for 30%, and North American facilities consuming the remaining 30%. These international sales bring substantial foreign currency into American coastal economies, with annual exports exceeding $100 million. The industry also generates significant tax revenue for state and local governments through business licenses, facility permits, and employee income taxes. Delaware alone collects over $8 million annually in horseshoe crab-related business taxes, funding coastal conservation programs and marine research initiatives. South Carolina has used industry tax revenue to fund educational programs, training the next generation of marine biotechnologists. The horseshoe crab industry faces mounting ethical scrutiny as environmentalists document alarming population declines across traditional habitats. Delaware Bay populations have dropped 75% since 1990, while climate change threatens spawning beaches through rising sea levels and shifting ocean temperatures. Conservation groups argue that commercial bleeding stress, combined with habitat loss, could drive these 450-million-year-old survivors toward extinction. Animal welfare advocates raise concerns about the bleeding process itself, questioning whether extracting 30% of an animal's blood constitutes humane treatment, even with careful monitoring and recovery procedures. While mortality rates remain around 10 to 15%, critics argue that any deaths for commercial purposes violate ethical standards, particularly when synthetic alternatives exist. The emotional impact on local communities adds another layer of complexity. Many collectors struggle with the knowledge that their traditional livelihood now threatens the very species their ancestors coexisted with for generations. The pharmaceutical industry defends current practices by highlighting LAL's unmatched sensitivity and reliability compared to synthetic alternatives. Recombinant factor C, a genetically engineered substitute, shows promise but faces regulatory hurdles and pharmaceutical company resistance to changing established testing protocols that have ensured drug safety for decades. The transition costs alone could reach billions of dollars, with no guarantee that synthetic alternatives will prove equally effective in all applications. Environmental scientists warn about cascading ecological effects beyond horseshoe crab populations themselves. Red knot birds, which migrate 9,000 miles from Arctic breeding grounds to South American wintering areas, depend entirely on horseshoe crab eggs for fuel during their Delaware Bay stopover. As crab populations decline, bird populations have crashed by 90%, demonstrating how biomedical harvesting impacts entire ecosystems. Sustainability efforts include controlled breeding programs, habitat restoration projects, and research into reducing blood extraction volumes while maintaining testing effectiveness. Some companies now use microfluidic testing that requires 100 times less LAL per test, potentially reducing harvest pressure while maintaining safety standards. These innovations represent hope for balancing medical needs with conservation goals. Regulatory bodies face unprecedented challenges balancing human health needs against species preservation. The FDA's acceptance of synthetic alternatives could reduce harvesting pressure, but transitioning pharmaceutical companies from proven LAL protocols to new testing methods involves years of validation studies and billions in compliance costs. Meanwhile, international pharmaceutical regulators move at different speeds, creating complex global supply chain challenges. What responsibility do we bear for creatures whose blood saves human lives? Could our reliance on these ancient mariners teach us about sustainable relationships between technology and nature? Will future generations inherit a world where medical miracles depend on exploiting Earth's oldest survivors? The answer may determine not just the future of horseshoe crabs, but our approach to biological resources in an age of medical advancement. As we stand at this crossroads between progress and preservation, perhaps the real question isn't whether we can afford to protect these living fossils. It's whether we can afford not to.